Okay, so this is the last question before we do the lecture on specific heats for solids and liquids. This is my third attempt solving this question because it's so tricky. So I would like you to pay attention. 2 kilograms of water contained in the piston cylinder with the massless piston loaded with linear spring and outside atmosphere. Initially, spring force is 0 and P1 equals to P0 is 100 kilopascals. That makes sense because spring force is 0 and piston is floating. So internal pressure must be balancing outside atmospheric pressure. So internal pressure must be 100 kilopascals. Even if they had not given us this, we should have been able to figure out that internal pressure must have been 100 kilopascal initially. With a volume of 0.2 meter cube. If piston just hits the upper stops, the volume is 0.8 meter cube and temperature is 600 degrees Celsius. Okay. Heat is now added until pressure reaches 1.2 megapascals. Show PV diagram, find work and heat transfer. Okay, all the usual things they've asked us. Except now there is a linear spring. So, if we see from 1 to 2, first the energy will go to increasing the volume. Right? But pressure here will not be constant because there is a linear spring. And after that, from 2 to 3, after the volume has become constant, the energy will start going to increasing the pressure. But in the question they've given us, as soon as the piston touches 0.8 meter cube, this volume becomes 0.8 meter cube, the temperature is 600 degrees Celsius. So at state 2 only we will reach 600 degrees Celsius. Right. So if we solve everything at 1, our V will come out to be between Vf and Vfg. Sorry, Vf and Vg. So it will come out to be a saturated mixture. And using V equals to Vf plus x1 Vfg, our quality factor at 1, x1 will come out to be 0.0584. And using this, our U1 will come out to be 538.475. At 2, our pressure is unknown because remember from 1 to 2 the pressure will not remain constant because there is a linear spring now, right? However, our temperature is known to us as 600 degrees Celsius and our specific volume is known to us at 0.8 by 0.1. So this is 2 kg, right, by 0.2. So it will come out to be 0.4 meter cube per kg. So what we can do is we can find the pressure at this temperature and this pressure and this specific volume, sorry. So at 2, if we find the state, it will come out to be superheated vapor. And if we refer to the thermotables, if we refer to the superheated thermotable specifically, our P2 will come out to be 1000 kilopascals. Right, let's see how that is happening. I have to go to superheated water tables. So if we see at 500 kilopascals and a temperature of 800 degrees Celsius, right? Is it 800 or 600? It is 600, right? At 500 kilopascals, 600 degrees Celsius is 0.8, then it is 0.66, then it is 0.50, then it is 0.40. So only at 1000 kilopascals the condition is met that 1000 kilopascal and 600 degrees Celsius the volume must be this much. So we know these two, that means this one must be 1000 kilopascals. So our P2 comes out to be 1000 kilopascals from the superheated tables. And at 3, P3 is 1200 kilopascals, that is given to us in the question. And since T sat at 1200 kilopascals is 187.99 and our T given is greater than T sat, that means it is still superheated. So U3 will come out to be 3295.6 kilojoule per kg. Right. So delta U will come out to be 5514.25 kilojoule, but W will give us some issue. So to find W when linear spring is involved, what we do is we draw this diagram. This is 1, this is 2, this is 3. If we notice carefully, the linear spring is causing the pressure to increase linearly from 1 to 2, right? So this was 100 kilopascal and this was 1000 kilopascal. And this was 0.1 or 0.2 something, 0.2, and this was 0.4, right? So work can also be calculated using area under PV graph, right? Or area of this trapezium. So area of this trapezium is given by half P1 plus P2 into capital V2 minus capital V1. Remember, capital V, not specific V, right? And if you calculate this properly, using these values and multiplying them by mass over here and doing all that, you will get work to be 330 kilojoule. And after that, you'll be able to find delta Q from this equation as well. It will come out to be 5844.25 kilojoule.